Okay, so let's go on with this final example that I talked about, namely the equation of energy conservation. So the question is, could we, from the Boltzmann equation in this form, could we also derive the equation of energy conservation, the one that we got from the stress energy tensor back a few weeks ago? The question is this possible? And the answer is yes. So using exactly the same type of machinery that we did for this number conservation, we can do exactly the same thing. So the question is, how should we write it out? The answer is we should just take not the very lowest moment of the Boltzmann equation, but the one where we multiply with energy. So if we start just like before, we do this momentum space integration, then we have the Boltzmann equation in here, like this. But now, instead of just doing this integral, we multiply with the energy of each state. And then we set this equal to 0. Now we can do exactly the same as we did before. So the first term, that is very easy, right? Because again, we can now remember, this is something that I maybe didn't say before, but it's important, of course, to notice this is co-moving momentum such that it's invariant under time. And that means we can now take out this time differentiation, and then this term will lead to a term which is just equivalent to rho dot, just like we did n dot before without the multiplication with energy. And that leaves us this one term which we treat the same way as before. Now we rewrite the momentum space volume, we replace it by 4 pi p squared dp. So again, we use the fact that it's spherically symmetric such that we can do the angular integration trivially. Then this is the momentum volume element. Then we have minus from here, and then p times e now df dp, like this. And again, just like before, we do it via integration by parts. And just like before, it's important, of course, that the boundary term goes to 0. So this will actually be equivalent to minus, which eats that minus sign. And of course, now I'm also missing a factor of the Hubble parameter. So this minus sign eats the one that we got from integration by parts. And then we are left with something that looks the following. So now we have, again, the 4 pi here. Then we have p cubed times e dp, and then f, and then the Hubble parameter we can take outside. So that's what this term looks like. And now we see, when we do this differentiation, we get exactly two parts. We get one which is 3 times p squared times e plus p cubed d by dp. This term here, when I do that integration, I collect quantities back, then I notice the factor of 3, I notice the factor of e. So this actually, when I do the integration, leads to exactly 3 times h times rho. And then we only have the final term, this one here. But remember that energy we can write in this way from the dispersion relation. And that means that dE by dP, that is 1 divided by 2 times energy, and then we differentiate p squared, 2 times p. So I can write that as p divided by e. So this term actually becomes not dE by dP, but p to the 4 divided by e. And now we're almost there, because the only thing that we now need is to notice that pressure is actually also a momentum space integral just like the one for energy density. The only difference is that the factor I have to multiply with is p squared divided by 3 times the energy. And then this factor here. But now, notice, this p to the power 4, that's a p squared from the momentum space element, and another p squared divided by E that looks exactly like the one for pressure, except for a factor of 3. So this actually turns out to be 3 times h times p, and then we're sort of happy because now we can collect this term, and that term. And that altogether gives us an integrated equation that looks like this, which, as you'll notice, of course, is exactly equivalent to the one that we got from conservation of the stress energy tensor. But that means we can also, again, rederive this from the microscopic point of view by starting with the Boltzmann equation. And one can also, and we'll show that later in the course once we get to deviations from homogeneity and isotropy, one can also derive the Navier-Stokes equation, for example, from the Boltzmann equation. And it turns out that the Boltzmann equation contains, that's not surprising perhaps, way more information than the macroscopic fluid equations, because actually what happens, and let's just sketch it very, very briefly, right? The continuity equation, that comes from the 0th moment of the Boltzmann equation. And now I'll just write it in the more schematic form, like this. Now, I haven't said anything about what this differential operator actually looks like, so it might be homogeneous and isotropic, and it might not be, right? So this is more general. Then if I multiply this with nothing, so to speak, then I get the continuity equation, which in the limit that we have seen it so far, in the limit of homogeneity and isotropy, is this equation, right? That's number conservation. Now I can also do higher moments. So for example, I could now multiply with a term which is the same dimension. It's just pi, spatial momentum, divided by 0 component of 4 momentum, like this, which incidentally you would also know as velocity, right? So that's the first velocity moment. That actually gives us the Euler, or as we also know it, the Navier-Stokes equation. But there are way, way more terms. In fact, there are infinitely many terms that I can do in this way. So I could construct a next term, which is then pi pj p naught squared, like this. And that is actually not an equation which is known in normal classical fluid mechanics. So you can think of this as something we could call an anisotropic stress equation, and so on and so forth. So in fact, I can get infinitely many of these equations, and one can show formally that the hierarchy, the so-called infinite hierarchy of different moments of that underlying Boltzmann equation, is equivalent to solving the full microscopic Boltzmann equation. So you can think of this as an expansion in an orthogonal set of functions, so to speak. So all of these terms, they all live in real space. They don't live in momentum space, right? They are momentum integrated. However, the infinite hierarchy here actually contains all the momentum space information, because they weigh momentum space differently, and therefore they are equivalent to doing the full Boltzmann solution, which, mind you, of course, is in the more general case is really complex because it's a function of 7 different variables. whereas these equations are functions of 4 different variables: spatial, location, and time. And in some cases, it's easier to deal with these equations. In some cases, it's actually easier to deal with the underlying Boltzmann equation. That depends very much on the setting that we're after. Okay, so having said that, then the next item on the agenda is to start looking at the right-hand side of the Boltzmann equation. You've seen the left-hand side, if we have particle conservation, is really trivial, right? It's just number conservation, nothing more. So all the interesting physics in the limit where we have homogeneity and isotropy comes from the right-hand side, comes from the fact that there might be other species that the particles you look at can interact with and exchange energy and momentum, maybe number also. So we need to be able to treat that.